talking about the sequences of random variables. So till now, what we have discussed are one, okay, yes. So again, I'd write so random variables. We have discussed these. So these are a mapping from the sample space to the real line. We have discussed complex random variables. Sorry, first we have discussed two random variables. Mapping from the sample space R square, complex random variables are a mapping from the sample space to the complex plane. And then we have discussed random vectors such that the random vector, so let's say x, omega to Rn or C. So a random vector is a mapping from omega to Rn or Cn. So now let us consider the case where each outcome of sample space is a sequence, or let me consider a sequence random sequence that is a mapping from sample space to let me consider a sequence that is a mapping from the sample space to R to the power infinity or C to the power infinity. So for every outcome in the sample space, I generate a sequence. I generate one realization of the sequence Fine. And so for every omega, so for every omega that is an element of the sample space capital Omega, I generate xn omega and I represent that as, so now the outcome, the sequence is a function of both n and omega. Fine. So a random sequence is not only a function of or is not only a function of the specific outcome of the sample space, but it is also a function of time. So is this clear, or you guys have any questions with this? Or is this definition of the random sequence clear, or should I elaborate on this more in some aspect? Gandhi, Yash, is this okay?
Yes, sir.
Yeah, great. So I'll continue then. So also can write, say I can define for a given sequence x of n, not underline, some or rather right. So W is entry of random sequence, fine. So W is an entry of a random sequence, and for any given value outcome in the sample space, W will take a specific value, or W is a W is a random variable. Fine. So W is a random variable. So I can say that in case of a random sequence, any outcome omega generates a of so in case of a random sequence, any outcome generates a deterministic sequence. So see, as we have discussed, random variables, random vectors, all of these are deterministic mappings. So any outcome will generate a deterministic sequence, that is true, and a random sequence can also be seen. So I can define this W, I can define any number of variables. So I can also see a random sequence as a sequence of random variables, right? So there are two possible definitions of a random sequence. That one, it is a sequence of random variables. Two, it is one deterministic sequence that comes out of a random experiment that is being mapped to the space of sequences. Fine. So are these two definitions of random sequences okay? Guys, are these definitions of random sequences okay?
Yes, sir.
Yeah, great. So we have two definitions of random sequences that are given like this, and now another question. If I look at sequence of general comma. So if I look at a sequence in general, isn't a sequence of anything isn't a sequence of real numbers or of complex numbers the same as a discrete isn't a sequence same as a discrete time signal? Guys, tell me, is there a difference? Is there some big difference between a sequence and a discrete time signal?
No, sir.
So basically, we started so this gives us a recipe for random discrete time signals. Now, if we can define these for random discrete time signals, naturally the next step would be continuous time signals. Fine. So I define a random process or a stochastic process x of t as a mapping from the sample space to the space of signals, and similarly we can define xt is a continuous time random signal where one realization of xt corresponds to one outcome, the sample space, and is a xt is a continuous time random signal where one realization of xt corresponds to one outcome in the sample space and is a deterministic signal. This is one definition of a random process or a stochastic process. The second definition of a stochastic process is xt is a random process if xt naught or xti for all I or xti for any ti is a random variable. Fine. So yeah, there is a sync error. This will go away. Or there is a my Wi-Fi isn't that good. Because of that, the screen is slightly distorted. Oh, okay. Yes. So fine. So any questions with the definition of a random process? No questions. Great. So now example. Let us take an example. Let K be the outcome of the roll of a die. Let K be the outcome of a roll of a die. Therefore, K is right, but K is random. Let xt, or since we are using capital or uppercase letters, K, K. Let xt equal sign some fixed, then is xt so is xt a random process? Except when rather, let me put it this way. So I change the xt, it will appear in a second. So my question remains the same. Is xt a random process, or how does xt satisfy the two definitions? Come on. Or rather, does xt satisfy the two definitions? Ashwin, does xt satisfy the two definitions?
I think it satisfies the second definition, like because XTI random.
Yeah, it will be random. XTI,
But
XTI.
yeah.
So given a k is one realization of the sample space is 1, 2, 3, 4, 5, 6.
Yeah.
K is one realization of the sample space. Once you know that k, it's a deterministic function, right? Given a k, xt is a deterministic function, right?
Yeah.
So that is one definition of a
Okay.
random process, and this is the other definition. So Bala, happy? Bala? Bala isn't here to
Sir.
teach things. Yeah. So makes sense, this one?
Yes, sir.
Great. So these are called random signals or random processes or stochastic processes. So now, like we had the probability density, CDF, all that of random variables, random vectors. So let's try to do that for random processes. For random processes, or processes, the notion. Hold on, my laptop doesn't like being kept on a table. The notion of CDF becomes slightly, or actually too cumbersome, not slightly. So this becomes too cumbersome to handle. So instead, we only deal with PDFs and we talk about the joint PDF of X for the mth order or nth order. So I'll define this in a minute. So for any n the set of natural numbers, thankfully this is in the set of natural numbers, and any choice of t1 to tn. So any n tuple t1 to tn in R, the joint PDF of xt1 is known and this is called the mth order PDF of. Fine. Or since we don't deal with the CDF, these are called the mth order statistics. We can obviously torture ourselves with higher order integration to calculate these things, but that in most cases isn't worth the effort. And thankfully, most practical purposes in comms, we are happy with the second order statistics. That is fine. Now, functions of random processes, or rather, I'll use the specific averages in random processes. So, we define the mean function of a random process as a deterministic function of time such that for all t, mu x of t equals expectation of x of t equals x of t f, or rather, let me use only x here, t fine. this is easily function of time. Fine. And the second function that or the second average that we'll be interested in is the autocorrelation function. We write it like this: Rx t1 t2 equals expectation of t1 x. Yeah, so there is something intentionally missing here. Tell me what it is, and I'll be happy. Bala, what is missing here?
Yes, sir.
Yeah, what is missing here? In the definition of autocorrelation,
That
I'm
it
intentionally
is
missing.
not displayed, sir. That means.
Oh, I'm sorry. I'm sorry. So let's hold on for a few more minutes. Don't know why my Wi-Fi is behaving so badly. Now is it visible? Bala, is it now? It's visible on my second screen now, so it should be visible to you as well. So, is it visible
No,
now?
sir.
Oh, bad. So what's the last thing that you see? I'll unshare and reshare perhaps. Oh, whiteboard crash. Wow, crashed. Wow. Hold on. Whiteboard is loading. Yes. Visible now, Bala? It's coming. Is it visible now?
Yes, sir.
Yeah, so what am I missing here? It's fairly obvious. Okay, hint. If X is a complex valued random process, then maybe you'll be able to guess it better. I'll tell you that X is a complex valued random process.
So,
This is hint.
conjugate.
Yes, conjugate. X2 should be complex conjugated. Yes. And this equals minus infinity to infinity, minus infinity to infinity, x1, x2, fx t1, x t2, x1, x2, dx1, dx2. This beast. Fine. So based on these, we can have, or based on these definitions of statistics of random processes, we can have certain properties of random processes or certain special random processes, but I'll call these properties of random processes. So the first property that we will discuss is stationarity. random process is called stationary. If its property, its statistical properties to be specific, statistical properties are independent of time. That is, if the that more specifically it is called nth order stationary if xt1 equals, or if it's nth order PD, I'll write it first. It's called nth order stationary if it's nth order PDF is independent time that is the PDF, the joint nth order PDF remains unchanged if shifted, if the reference points, the reference points are shifted by a fixed amount. That is, let fx1t xnt x1 till xn be the PDF of let x1 till xn be the PDF of the nth order PDF. Then if this is equal to x1 t plus delta xn, oh sorry, not this, xt1, my bad, xt1 xtn xt1 plus delta x tn plus delta x1 to xn. So if the PDF remains unchanged for all delta, for all real delta, if this is true, then the random process will be called stationary. And random process is called cyclostationary if the is periodic, or is called nth order cyclostationary. we'll use cyclostationarity later. Nth order cyclostationary if it's nth order PDF periodic in time. That is f t1 plus delta t1 plus kt x tn plus kt equals.
Excuse me, sir.
Yeah.
That I think there aren't supposed to be subscripts up on the top, x1, t1, and xn, t1 in the random variable notation.
Yeah, so xt, so no, these so these are x1 to xn are dummy variables. You can put y, you can put z, you can put anything you like there.
Okay.
Okay. Thank you. Otherwise, so xt1 to, so these x1 xn equals t1 x. Yeah, one problem with this part is that it becomes too cumbersome to write too easily. Fine. So for some fixed period t and k being an integer. So the fun thing is that otherwise a random process or random process whose statistics change with time are is called, not are called, is called non-stationary. So the nth order or nth order, yeah, the nth order stationarity becomes too cumbersome to handle, and since we said that we are happy with the second order statistics for most communication signals, so we'll define the second order statistics and be happy with this. So a random process is called second order stationary or stationary in the wide sense. So it is called stationary in the wide sense or wide sense stationary if one mu x of t equals some m, if its mean is a constant function of time 1, and 2, its autocorrelation function is only a function of the lag between t1 and t2. Or in this case, I can define, oops, purely a function of the lag, rather than, so the autocorrelation function is purely a function of the lag and not of the absolute locations, the time. Fine.
Sir, is that
And
T or tau in that equation?
which one?
Like
So
Rx
yeah,
plus tau by 2. It looks like T or tau.
T plus tau by 2, T minus tau by 2. This is tau.
Sir, in
Tau.
RHS
Fine.
it is tau or T.
Tau, tau.
Means have you changed it? Means I can't see it.
Okay, so no, it is tau. So I've made it clear. So it will appear in a while. My Wi-Fi is lagging again. Sorry. Fine.
Yes.
So is it visible now?
Yes. Sir.
Yes, it is visible. So fine. So this is only a function of t minus tau. Similarly, xt is cyclostationary or wide sense if this is periodic, the mean is periodic. And this again this. So more specific definition of cyclostationarity we will cover at a later point of time. Fine. So now we have described what's wrong with this? Yeah. Okay, so we have described the time domain analysis. So random process, or rather I would put it this way. So a random process is a signal, and when we talk of signals, it is natural to wonder about their frequency domain versions. But since xt is random, it does not lend itself to frequency domain analysis that easily. So instead we analyze the frequency domain is of the statistics before doing this. Redefine before we launch into this, let us redefine the autocorrelation function as, this will maximize in a moment. Let us define the autocorrelation function as Rxx T1 T2. Instead of this, let's write, this is a more convenient notation such that T equals T1 plus T2 by 2 and tau equals T2 minus, or tau equals T1 minus T2. And we can write Rxx simply as equation of x tau by 2 x conjugate t minus tau by 2. Right? This is a more convenient version of, or more convenient definition of the autocorrelation function, which is naturally so when process is Whiteson stationary, Rxx t comma tau this semicolon equals Rxx tau simply, and when it is Whiteson cyclostationary, God, this is embarrassing. When it is Whiteson cyclostationary, fine. So this is a definition of the autocorrelation function, and with this definition of the autocorrelation function, okay, so it's almost time. So I'll just define something and stop. With this definition of the autocorrelation function in hand, we define the power spectral density as Sxx t comma f equals minus infinity to infinity Rxx tau j2 by f tau d tau. This, and in the special case when the process is Whiteson, God, is this happening? And in the special case when the process is Whiteson stationary, then I can send if so this is a bad day, right? So let's write this and let me close this discussion then. Maybe my laptop will cooperate tomorrow. So when xt is Whiteson stationary is no longer a function of time and is simply defined as f tau t tau, or the Fourier transform of the autocorrelation function over the lag, or the Fourier transform of the autocorrelation function in the lag domain. So we will stop here and continue discussing the power spectral density tomorrow. Any questions?
Sir, when will we discuss the mid-sem questions?
Good question. So, okay, yes, that leads me to a side announcement that there will be no tutorial this week. That is there. So, this Friday, mid-sem, this Friday, or so most probably this Friday. Is that okay?
Yes, sir.
Yes.
Great. Yeah, great. Okay. So, okay then. I'll try to upload all the checked answer scripts before that, so you can simply look at your answer scripts before we discuss the questions. So maybe you'll get to some idea. Fine. I'll try to upload and I'll ask my TAs to add those to the Excel sheet as well. So I'll first possibly share the answer scripts and then the Excel sheets. Is that okay? Yeah. Okay then. Bye. Have a nice day, all of you. So today was lecture 20 for the record. And we are 2 lectures behind, because of the introductory class and the other because of that code tantra nonsense. So I want to cover this up maybe